So if the number was added.
All right, happy Friday. So end of week 4. This quarter's going really fast for me. I don't know about you.
Yeah.
It's like it's gonna be done really soon. All right, so I think most people turned in PA2. I had 65 submissions, and there's 67 people on the roll, but I think a few of them aren't actually like taking the course anymore. They just haven't dropped. So everybody happy with PA2? Yeah? Cool. All right, looking forward to seeing what you did. So I will get those graded over the weekend. I also have 215 homework coming in today, so I got a lot of grading to do, so it may not be until like later Sunday.
You can push back that?
Push back 215?
Yeah.
You'd be disappointed. So any questions? I'll go through the code on Monday. There's not much to show actually, but any questions on anything up to here, including PA2? I've had some questions from people regarding malloc, and particularly if you're using Valgrind and you're getting memory leaks. I'm seeing things like this pop up in code sometimes. So this is, I don't know, maybe our search function. So you're searching for a number inside a list, and list is a pointer to the sentinel. So I've seen code where someone says struct node star temp equals malloc blah blah blah, and then temp equals list arrow next. And right there you've got a memory leak, right? The reason is that when you do this, anytime you do malloc, you're drawing a rectangle. Okay, if you keep going back to your pictures, every time you do malloc, you're drawing a rectangle. And in this case, when you take a pointer and you set it equal to something, you're writing down a label. So when I say malloc size of struct node, I'm making a rectangle. When I say struct node star temp equals, I'm saying temp is pointing to this rectangle. And list is coming in, so list is another rectangle that already exists. That's what our function was passed. And when I say temp equals list arrow next, what I'm saying is temp is the name of this rectangle, and this rectangle has been abandoned now. Right? There's nothing pointing to it, there's no way to free it, it's going to be a memory leak. So the only time you really want to use malloc is if you're thinking of your pictures when you don't want to make a new rectangle. Okay, if you want to refer to a rectangle that's already there, all you need is a struct node star variable, and you can say variable equals whatever refers to that box. So malloc always makes a new box. And this will come up in object-oriented design when we do Java. Instead of malloc, we'll use the keyword new, but it's the same idea. We'll be creating a new version of an object. Sometimes you want to do that, sometimes you just want to refer to an object. All right, well, let's talk about PA3 then. So PA3 is posted. So as promised, this is an assignment that deals with stacks and queues. Okay, so we've talked about stacks and queues. You're going to implement them using lists. So stack, you can make a list, insert in the beginning. Queue, you insert at one end, remove at the other. The main program is a little different here from what it was for PA1 and 2. We're not just working with a single data structure like a list. We're working with two structures, a stack and a queue. They're totally separate from each other. They both exist at the same time. So we need to tell the program which structure we want to manipulate. What we can do is we can add things to these structures. We can remove things from these structures. But we need to tell it which one we want to work with. So this main program is going to be stateful. It always sits in one of two modes, either stack mode or queue mode. Okay, if you're in stack mode and you say add an item, it gets added to your stack. If you're in queue mode and you say add an item, it gets added to your queue. Okay, so your first two commands are S to say go into stack mode and Q to say go into queue mode. These are also how you print the contents of the stack or the queue. So if you type the command S, it should print the current contents of the stack, printed on one line, top of the stack on the left. And then change your mode to stack mode. If you're already in stack mode, you don't have to do anything there. But you still print the stack. If you type Q, it prints the current queue and asks for the head of the queue on the left, tail on the right, and then put your mode into queue mode. So S and Q do two things. One, they're used to examine the stack or the queue, and two, they're used to change into that mode. Okay, whichever mode you're in, if you type in a number, it gets added to the stack or the queue, depending on which mode you're in. Stack gets added to the top, queue gets inserted at the tail. And then P either says pop the top of the stack or remove the head of the queue and display it to the user, take it out of the structure. And then big Q quits and frees all of your memory. Anything else gives you a help message. So there's a sample executable version of this program on the Linux server. It's under /temp/pa3 sample. So you can run this and get an idea of what I want your program to do. Okay, so a number inserts into the stack or the queue, S and Q, etc. So let's start off in stack mode. It tells me it's switching to stack mode and the stack is empty. So let's just push some things onto our stack. So we'll push on prime numbers. So we got 5 things on the stack. If I want to look at the contents of the stack, I can just say S, and it tells me that's what my stack looks like. Top of the stack is 11, that's the last thing I pushed. If I go into queue mode, let's put some more primes in. And now look at our queue. Bless you. And the head of the queue is 13, that's the first thing that we inserted, the tail is 29. Okay, so I can go back to stack mode, and I don't remember what my remove command is, pop. So if I hit a P, that gives me my 11. That was the last thing I pushed. If I hit P again, it gives me a 7. And if I want to look at the stack, I can just say S, and it tells me my stack now has 532. If I go back to queue mode, and I say pop, it should give me the first thing that was put into the queue, which was the 13. So there's my 13. And my queue looks like that. And if I pop again, there's my queue, and so on. Make sense? Yes?
Should we default to one mode or the other?
I asked you to default to stack mode. But I didn't put that in the original assignment. I put it in and reposted it like 30 seconds after the first. So if you're really fast, it didn't say that. Yeah?
Why does it say switching to whatever mode? Is it going out of the mode after you execute?
You don't have to actually say that, but it's just letting you know that if you do a queue, you're now in queue mode. It didn't actually switch to it, so I should say in queue mode now, or something like that. It's just letting you know you're in queue mode. You could change the prompt, Q colon or S colon or something. That would be fine. All right, so let's empty out our queue. So our queue is empty right now. If I try to remove one more, it says error, queue is empty. Okay, and I can do that as many times as I want. It should not segfault or kick me out. And it should never corrupt the stack when I'm in queue mode and vice versa. So I can pop off the 5, the 3, and the 2, and my stack is empty, and if I try to pop off anything more, it tells me stack is empty. That's pretty much it. And then Q gets you out. So the main program is like I say, a little different from PA1, PA2, but same kind of thing. You're going to read a command, you're going to print a prompt, you're going to read a command, you're going to parse it various ways using scanf or if statements, looking at character 0 probably, and then you're just going to call whatever function you need. And the only slight twist is this idea of having two modes, because when you say P, you might want to call the remove function for the Q, you might want to call the pop function for the stack. So you need some kind of state variable that's really just a flag. It says, am I in stack mode or Q mode? So when they say P, if I'm in stack mode, call pop, otherwise call remove. If they type an integer, if I'm in stack mode, call push, otherwise call insert, or whatever you decide to call your functions. And then S and Q just change that variable.
So the way to do use array linked list or malloc linked list?
Definitely malloc to linked lists. Yeah. Yeah, pretty much any time we do a linked list, do it in the style of PA2, not PA1. PA1 was purely academic exercise. All right, so implement both of these using a linked list. So you got two sentinel nodes, right? One pointing to your stack list, one pointing to your queue list. For the stack, I'd like you to push new elements by adding them right after the sentinel. So here's your original list. This is your sentinel. If you want to push a 2, your list should turn into that. If you decide to push a 3, your list should turn into this. Right, sentinel points to a 3 and that points to a 2. If you push a 5, sentinel points to a 5. 5 points where the sentinel pointed, and that points to 2. So this is just your add function, but instead of searching for a magic place to add your node, you just add it right after the sentinel. So it's a kind of simplified add function. For the queue, the head will be the node right after the sentinel, and the tail is at the far end. So for a queue, so here's the sentinel, this is the head, this is the tail. So when you want to add something to the queue, you start at the sentinel, you go all the way to the end of the list, and you tack it on out here. And that becomes your new tail. And when you want to remove, just remove the thing right after the sentinel. So a slightly different version of your add function and a simplified version of your delete function. So let me, well, I'll come back to this in a second. So notes, you probably won't run out of memory unless you have some really egregious, malloc loop or something like that. But it doesn't hurt to check malloc's return to make sure it's not null. Do that in general. If you try to remove from an empty structure, give an error message, but don't do anything else. Don't exit the program. Don't let your sentinel get deleted or anything weird, right? It's just a user error. Don't disturb your data structures. And moving from one mode to another doesn't actually change anything. Don't free all the stack memory just because you're moving into queue mode. Okay, keep both things pristine until you exit. When you exit, call some kind of free function to clear all the memory. Okay, so that valgrind doesn't give you any issues. Lots of comments. A make file, please. And I would like you to call your executable program PA3 this time. Okay, instead of main or anything else, just make the executable PA3. And then wrap it up in a tar, submit it to Canvas, you're good to go. And look at this, it's a one-page assignment. All right, so questions about PA3, what you're expected to do. Yes?
Do you have any specifics on how you want us to form the functions? Is that
Totally up to you. But I would be surprised if you turned in one main program that did everything inside there, right? So hopefully it'll make sense to you to have, you know, a set of functions for adding to a queue, pushing to a stack, popping from a stack, removing from a queue. And you probably want to take your linked list code in some form and reuse that, right? And so you may have a separate layer of functions just for manipulating linked lists, and on top of that might be your stack and queue functions, and on top of that is your main program. But see what makes sense, right? Think about the organization of this before you actually start writing code. Think about, you know, you're sitting behind a big desk and you're going to just hire people to write code for you, but what do you want them to write? What kinds of modules? So do you need an init module? Do you need an add module? Do you need some function for handling this mode switching? Think about it from kind of a high level and just sort of scratch out on paper what functions you would like and what those functions might have to call and what those functions might call and so on. And organize it like that and then start writing some code. All right, let me make a comment. For the queue in particular, and so as we get more advanced, our rectangles become circles. So there's the head and there's the tail. I haven't gotten this backwards yet this quarter. I'm really surprised. Headed right after the sentinel. Good. Okay, so here's the head and here's the tail. So if you want to remove, it's easy. You just start at the sentinel, get the value from the next node, have the sentinel point where the next node points to skip over that, and then release whatever that next node was, free it from memory. Okay, for the tail, you've got to somehow get to the end of the list, and you've got to remember the previous node and make sure that previous node points to null now, and then free the tail. If you like challenges above and beyond, there are more efficient ways to handle the tail. Right? One thing you could do is you could have a doubly linked list, and you're welcome to use that approach if you like. A lesser approach that works equally well, though, is to keep a pointer to this node or to the tail and use that to actually we're inserting at the tail, so keep a pointer to the tail, and then when you want to insert you have to do two things. One, use that pointer to the tail to say, okay, change this thing so instead of pointing to null it points to my new node. And then update this pointer to point to your new node. So you can introduce one more variable called a tail pointer. And when you want to insert, this always gets you to the last node, so you make that point to a new node. And then set tail pointer equal to this new node. And it's a fixed set of operations no matter how big your queue becomes. And your tail pointer can actually be part of the sentinel if you like. So you don't have to make it a global. And you can redefine the node structure with a tail pointer in it and just use that in the sentinel node. So there's things you can do here. I used to make this a part of the requirements, and I decided to take that out because I want you to concentrate on the other aspects. But like I say, if you like a challenge above and beyond, think about how you can make it more efficient so that if the list is 1,000,000 nodes, you don't have to go through 1,000,000 nodes to figure out where the tail is. And it'll get you into some different mindsets about pointers and structures. All right. Any other questions about this?
Do you need free memory after take off the stack?
Yes, after you remove something from the stack or the queue, definitely release that memory right then. Otherwise, you have no way to get to it later. Right? Once you pop it off the stack and you basically delete it from the list, if you don't free it then, it's lost. So yeah, same as in PA2, free it right away.
We also free for queue too.
And for the queue, yes. Yeah, your goal is at the end when you exit, there should be no leftover memory allocated. So unless you can free it at the end, make sure you free it as soon as you don't need it anymore. So both stack and queue. All right, well, why do we care about stacks and queues? We've talked about some applications and operating systems and in doing homework and dealing with fires. But let's look at classes of problems where we can use these kinds of structures. So there's a classic problem called the n queens problem. And so how many people here play chess or know how to play chess? All right, cool. Oh, that's awesome. That's really cool. So here's a classic problem. So the queen is like the all-powerful piece on the board. For some reason, you don't lose if the queen dies, though. That never made sense to me. But the queen can basically move in any direction, diagonally, horizontally, or vertically. So if you have a queen sitting right here, it can attack any piece in this row, any piece in this column. It could attack this piece right here because it's diagonal, or any of the pieces along this diagonal. All right, so assuming there's nothing blocking its way, it can move in basically 4 directions. All right, so the question is, can we place 2 queens on this board so that they don't attack each other? And it's pretty easy to do. So if we put a queen right here, right, and you look at all the places they can attack, they can't attack each other. Okay, can we add a 3rd queen that won't be attacked or attack any of the others? And you can do that too. And so the question is, how many queens can you do this for? And you can't do it for 9, right, because there's only 8 columns on the board. If we have 9 queens, at least 2 will be in the same column, and they'll attack each other. That's something called the pigeonhole principle that we'll talk about later. But it turns out you can do it for 8 queens. You can place them on the board in a way that they don't attack each other. And so it's an interesting puzzle to try to write a program to find solutions to this 8 queens problem. And we can do it with some nested loops, but that's just because of the nature of the problem. More generally, how could you go about trying to do this? Well, you could start off with 8 queens. So first of all, let's number the positions on this board. So this will be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right, all the way down to 63. Should have been 4 because I started from 1. All right, and so on. So number the positions in some way, and start off by just putting your queens in the first 8 positions. And say, is this a valid solution? And it's definitely not. Right, they're all able to attack each other. So we have to move at least one of these queens. Which one should we move? Well, we could move the one that we placed last. So we could pick up this queen who's in position 8, and take them out of there and move them to a different position. Let's move them to position 9. And now do we have a solution? No. So we can pick that queen up and move it to 10 and keep doing this. And clearly none of these are going to get us a solution because, the problem is back here. But eventually we try putting this queen in position 64 and it's still not a solution. So what can we do next? We've moved this queen into all possible places. Assuming these 7 queens are in these positions, we got to change something in this part of the solution, right? So we placed queen here, 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 and here. Let's take the 7th queen and let's move it down 1 spot. And then put the 8th queen in the next spot. And see if that solves it. And if not, we'll move this queen here and so on. And in the end, we won't find a solution, so we'll go back and we'll say, okay, well, let's take this 7th queen and let's move it down another spot. Let's put it in box 9. And then look for a solution. And we'll keep doing that until eventually we put this queen in box 63 and the last queen in 64, and we don't find a solution. So we've got to do something to this. So we'll go back and we'll say, okay, well, the 6th queen, instead of putting it right there, let's put it down here. And assuming that we're not very observant, right, and we just do this dutifully, we're going to go through a lot of iterations, but eventually we'll have tried every possible placement of queens, and if there's a solution, we'll find one where nobody's attacking anyone. So the question is, how can we code this kind of algorithm into a program? And like I say, you could do it with some nested for loops, but it's a bit of a cheat because here we've got, numbers associated with these positions. But we can use a stack to achieve the same idea. So the idea would be, when we place a queen, we push its position onto a stack. Okay, so here's our stack. And we always have to indicate how we're drawing our stacks because there's so many ways to do it. So I'm going to add things from the bottom. So the thing up here is going to be the first thing I put on the stack, and the last thing I put will be at the bottom. So I would push on positions 1, 2, 3, 4, 5, 6, 7, and 8. And I check for a solution, and it's not a solution. So I'm going to pop off the last entry, add 1 to it, push it back on the stack. And now I'm going to try this. And if that's not a solution, I'll pop off the last entry, add 1, push it back. I'll do that for all 64 possibilities until I push to 64. That's not a solution. I'll pop it off, add 1, I get 65. That's too big. So at this point, I'm going to pop again. I'm going to add 1, push that on the stack, and then I'm going to push the next number on for the last queen. And I'll keep doing that process until eventually the last 2 entries in my stack are 63 and 64. I'll pop this off. 65 is not valid, so I'll pop this off, add 1, which gets me to 64, and when I try to push on my last queen, I'm out of space. So I'll pop off the prior thing, which is a 6, add 1, put a 7, and then I'll push in the next 2 entries, 8 and 9, and keep going. And eventually, after something roughly 64 to the 7th times, right, my stack would have looked like this. And it's not a solution, and I pop off the 64 and add 1, and that's invalid. And I pop off the 63, and if I add 1, that's 64, but it's not the last queen, so that's going to be invalid. I'm going to pop all of these off, and eventually I'll pop off the 1, add 1, make that a 2, and then I'll push on the next positions, and now I'm examining a solution where my first queen is in box 2, and my other queens are lined up right after that. And you go through the whole process, and eventually you'll pop that off and you'll come to a 3, where your first queen is in box 3. And you keep doing this until eventually your stack looks like this. Which is where your queens are all stacked up in this last column, and that's the last possible combination. So what are we doing? We're performing a search. We're trying to enumerate all the possible placements of 8 queens, regardless of whether they solve this problem. We're trying to find all possible placements of 8 queens. And then for each one, we're going to say, does this, solve our n queens problem? So we're doing a search. We're searching the space of possible positions. And a stack is a systematic way to do that search. And it's kind of the way that we would probably do it if we were doing this completely naively, right? We might put them all down here and we'd pick the last queen and try different spots, and that doesn't work. So we'd move this one and so on and so forth. But we could also do this with a queue. And with a queue, it looks fundamentally different. I should have brought in a chessboard. With a queue, we might start off with the 8 queens here. And if that's not a solution, well, we're going to take this first queen and move it to a different spot, because that was the first queen we placed on the board. And if that's not a solution, then we'll move that queen somewhere else, and we'll go through all the possible placements of that first queen. And if that doesn't work, then we'll go back and we'll start moving the second queen. And there's a dualism between stacks and queues when we're doing searches that is sometimes apparent in problems and sometimes not quite as apparent. So let's look at a different example. Let's think about a maze. So you're trying to run a maze. Let's say we're supposed to start here and exit here. I might have done it backwards. Yeah, I did it backwards. Most mazes, for some reason, there's like one way that's like really easy and one way that's really hard. So this way is harder. All right, so we're going to go in here and we're going to come out the top. So how do we do this? Well, we start going down the maze and we get to a point where we have to make a decision. Okay, so at each point we can either go west, north, south, or east. All right, so we get here, well, we're coming in this direction, so we're not going to go to the left. So we could go up or we could go to the right. Which one do we want to do? Well, let's assume we have some kind of order. So let's pick our order to be left, up, right, down. So we get to this spot. Okay, let's choose to go up. So we'll go up. We get to another decision point. We can't go left, but we can go up. Here's another decision point. We can't go left, but we can go up. We get to a dead end. Okay, that's not a solution. Well, what did we do at our decision point? So we got here and we went up. And then we got to another decision point and we went up. And we got to another decision point and we went up. And we hit a dead end. So we got to do something different. So I think most people probably come back to that last place and try something different. So we pop off this last decision and we say, okay, well, we went up and that didn't work. Let's try going to the right. So we push a right onto the stack. And we come through. Here's a decision point, so let's try going up first. So we'll push an up. And here's a decision point. We can't go back because we came from there. We can't go up, so let's try going to the right. So we'll push a right. And we hit a dead end. Okay, so we go back to the last decision point. We pop that off. We say we couldn't go right. Let's try going down. So now we come down, and here's a decision point, and so on. And it may be that after we do all of this, we don't find a solution. We've exhausted all the possibilities because we need to go back to this move that we made and do something different. But eventually, we'll have gone through all the possible twists and turns we can make, and if there's a solution, we should find it. So what does our structure look like on our stack? Well, we need to know what direction we turned, and we also need to know where we made that decision. So we need some way to identify places in this maze, and we also need to know which way we moved. So we need some kind of composite structure with like x and y coordinates and then a direction vector, one of 4 choices. And you can code this up and feed it a maze somehow, so it knows what's available at each point, and you can find a solution to it. Now we can also do this with a queue. So we start off in here, so this was a stack, let's do it with a queue. We come in here, we come to a decision point, can't go left, so let's go up. Here's another decision point, we can't go left, so let's go up. Here's another decision point, we can't go left, we can go up. We hit a dead end. Okay, so what do we do at this point? If this is a queue, we're going to go back to the first decision that we made and try something different. So we'll come all the way back here, and instead of going up, we'll try moving to the right. And we'll push that into the tail of the queue, and we'll move along and we'll add more decision points, and if we get to another dead end, we'll come back to this decision point back here. Right? And it's just, it doesn't seem to be the way our brains like to work with these things. But you can do it either way. And again, it's like the KVL, KCL thing. Some people think in terms of queues. The majority probably thinks in terms of stacks. And running a maze is just another search problem. Right? You can enumerate all the possible ways that you can move through this maze, and some of them take you to dead ends, a few of them take you to the exit. But the full reckoning of all the possible ways you can travel through here is just at each junction point, you have to take into account every possible turn that you can make. And you can represent this pictorially as a tree, right? At this first point, I can go up, or I could go to the right. If I go up, I get to another junction where I can go up, or I can go to the right. If I go up, I'll get to another junction where I can go up, or I can go to the right. At this first junction, though, if I went to the right, there's nowhere else I can go. At this very first junction, if I went to the right instead of up, I'll come to another junction right here, where I can go up or right. And you can build this structure, this picture that basically says starting from here, I can go to the top and I can go to the right, or I can go up, up, and go right, and so on. And some of these dead end, but some of these may lead to the exit. And if you had a picture like this, running the maze is equivalent to the question of how can I start from here and follow a path of these that eventually get me to the exit. And if it's laid out like this, it's easy, right? And in fact, if you start at the exit, you can just go up until you get to the beginning, and the solution just pops out right away. So this is something that's called a tree. This is what we're going to start talking about next week, our binary trees. And this process of enumerating all the possible ways that we can move through this maze, this is equivalent to trying to find all the possible paths that you can follow starting from the beginning of this tree, what we call the root. What are all the possible ways that we can go through here? If at each point we can go multiple directions, how can we travel down all the possible combinations of direction choices and know that we've covered every possible path. And that process is simply called traversal. Same term we used for going through a list and printing out everything in the list. If we want to go through a tree and print out everything in the tree, it's still called traversal. But it's a more complex algorithm because we don't just start at the beginning and follow the arrow. We've got multiple directions that we can go at each point. And how are we going to traverse? We're going to start off here and we're just going to go all the way to the left. And when we get to the end, we'll go back to the last point where we could have gone somewhere else, and we'll go somewhere else. And this might have multiple choices. So same thing, we'll go all the way to the left, and when we're done, we'll come back and we'll go a different direction. And so traversing a tree is basically like running a maze. But we're going to do it with stacks. But we're going to discover that we don't actually need to think about stacks when we do this. We're going to take a totally different approach to traversing a tree, and that's what we call recursion. So if you're in 215 right now, that's what we've been doing the past week. That's the backbone of mathematical induction and vice versa. And recursively, running a maze is going to be easy. How are we going to do it? We're going to come to this first decision point, and we know that we can either go here or we can go here. Well, we're going to draw a simpler version of this maze, and in the simpler version, we're going to put a wall right here. We're going to get rid of this little piece, and we're just going to have an entrance here. And we're going to hand this to a friend and say, hey, can you solve this? And if they can solve it, we'll take their solution and we'll superimpose it on here. We'll say, okay, we'll come in here, turn left, and then do what my friend did. And if they can't solve it, right, we'll take a version where we block off this wall, we remove this, and we hand this maze to a friend and say, hey, here's where you start. Can you solve it? And they find a solution, and we come back and we say, okay, here's our solution. Go straight at this first junction and then do what my better friend did. And that gets you to the exit. And so we never have to do any work, right? We just have to notice that there's two possibilities here and find two friends, give them two smaller problems, two simpler mazes, see if one of them can solve it, and then just steal their solution and say, okay, but at the first decision, go either up or to the right. And our friends, being very clever and having taken 222 and 215 themselves, do exactly the same thing. They don't want to actually do any work, so they come to the first decision point and they make a series of mazes and they hand those to friends and say, solve these. And they combine it with their first move. They've got the solution, they give it back to you. Okay, so that's recursion. And when we code that up, it's going to be a few lines of code, because you're not really doing any work. Right? You're just saying you can go either this way, that way, or this other way. See if there's a solution for any of those. And if there is, we're done. All right, so trees will tie into mazes and maze-like things. We do this when we browse the web, typically. So you're on your favorite browser and you go to Google and you type in hash functions, and it brings up a bunch of stuff. And there's a Stack Overflow page, there's a Wikipedia page, there's an advertisement for vitamins or something. And so you click on the Wikipedia page, right? And it brings up a page and there's lots of links in there and says it's code, so you click on code and goes through that and it brings up recursive function. You're like, oh, I heard about those. You click on recursive function, right? You're running a maze basically, because when you're done with that last thing you clicked on, what do you want to do? You want to go back to where you were and find something else to click on. Okay, so in the browser you hit a back button and it brings you back to that previous page I was talking about C code, and recursive function didn't take you anywhere, but there's a thing that says, pseudocode, and you click on that. So you're basically doing a stack-based traversal of the web page. Right, you're starting with the results from Google, and you're following a link, and you follow that further and further and further. And when you decide you've gone too far, you usually come back one level, find another link on that same page, and follow that. And sometimes you decide, this was a waste of time, I don't need better vitamins, and so you click the back button a bunch of times, and you get back to your original Google results, and you say, well, let's try Stack Overflow, right? And that's fundamentally the same process as what we're doing here, right? This is your home page, and these are the different things you can click on, and each of those pages has different things you can click on. And there could be, 15 things that you can click on some of these. So it's not always just a binary tree. But again, the question is, how do you navigate this so that you see everything that's available on here? And we can do it with the back button. If we remember where we were, when we go back to a previous page, we can just keep going down that page and find other things to click. And this gets complicated because, of course, in a web and in really nasty mazes, sometimes your links go back. Okay, that's not going to be a tree anymore. That's going to be something we call a graph. And we'll mostly deal with trees. We'll talk about graphs a little bit towards the end of the course or next quarter. But if you're traversing and you get down here and it takes you back up here, it's kind of like having a little open loop in the middle of your maze. You got to somehow recognize that, hey, I've already been here. I'm running in circles. So you drop your breadcrumbs. Or if you play adventure, you drop an item as soon as you get into the twisty-turny passages that all look alike, and then you know when you're back. All right, I don't have time to talk about stack-based calculators. Let me start on it, though. Anybody here familiar with reverse Polish notation? RPN? So when pocket calculators were first being developed in the 60s, I believe, normally they work the way that calculators work today. If you want to do 2 plus 3 plus 5, you say 2 plus 3 plus 5 equals. Okay, that's algebraic. Reverse Polish notation, though, the operation came after the operands. So if you wanted to do 2 plus 3, you would type a 2, and then you type a 3, and then you'd say plus. And then if you want to add a 5 to that, you type a 5, and you'd say plus. So algebraic notation is number, operation, number. Reverse Polish notation is number, number, operation. And it turns out this is really complex to try to analyze, and you need parentheses. Because if you want to do something like 2 plus 3 times 4 plus 5, you got to have parentheses there to say do these things first. Reverse Polish notation, you could say take 2, 3, add them, take 4 and 5, add them, and then multiply. No parentheses. And this, if we want to evaluate this expression, it's really easy with a stack. So you can make a stack-based calculator using reverse Polish notation. So we'll play with that on Monday and wrap up some comments on stacks and queues, and then we'll jump into trees. All right, that's all the time we got. I will see you next time.